So, good evening. So, this is Mansi Tripathi. I am TA for this particular course, Environmental Chemistry. So, this will be the seventh week of doubt solving session. There will be 12 weeks of these kind of sessions. You might have received the material for week 8th or 9th, but we are still in seventh week of doubt solving sessions. So, what I'm going to do is first, for the seventh week, we will see some kind of similar assignment questions. First, we are going to solve that. Then, after that, we'll see solubility equilibria, which is part of 8th and ninth week in detail. Okay, so week 7, the questions that we are going to solve, that is mostly based on buffering capacity, Henry's law, all these things. After that, we'll solve the solubility equilibria. So I'll start the session now. I'll share my screen. Okay, so I'll start the session. I think you need to open Visual Mintech for solving this particular session because this is mostly based on Visual Mintech, which is a software developed to solve such kind of solubility and pH equation related problems. So there will be problems in the forward as well as backward direction. Also, we'll be seeing some problems related to carbonic acid system, which is a real acid-based system in water. So we'll start the session now. Okay. So coming to the first question, a wastewater is simulated as an ideal solution containing 10 raised to power minus 2.5 molar NaHCO3, that is sodium bicarbonate, and 10 raised to power minus 3 molar ammonium chloride, NH4Cl. The utility hopes to remove nitrogen from the solution by volatilizing ammonia gas. So this is kind of real problem that we face in real life. Okay, so here is the utility who wants to remove the nitrogen from the solution by volatilizing ammonia gas. To prepare for that step, 148 milligram per liter of calcium hydroxide will be added to raise the pH. You can answer me in the chat box, why do we want to raise the pH to convert it into ammonia? Okay, this is the pH before and after lime addition. Okay, we need to find out the pH before and after lime addition. So what do we have to assume? That no calcium carbonate precipitation or ammonia loss takes place during lime addition. What will happen when we add lime? There will be increase in pH, so calcium carbonate may precipitate. But here, for the simplicity, we are assuming that there is no precipitation and there is no ammonia loss, means nothing is going into the atmosphere. All the species remain in solution. We need to choose the closest answer. So you will get this kind of question examination. This we can solve by using Visual Mintech. Okay, so you need to find out the correct answer. Please take some time, use Visual Mintech software and solve the correct answer. I will write one equation for you. So this will help us to know that why we need to increase the pH. Okay, ammonium ion, that is our ammonium chloride. When it is dissolved in water, it may dissociate into ammonia gas and H plus. So we want the equilibrium to go into forward direction. Okay, we want the equilibrium to go into forward direction so we can get more and more ammonia gas. For that, what we need to do, we need to reduce the H plus amount, so that only that will be the only case when equilibrium will move in forward direction. We need to reduce the H plus, and how we can do that? By increasing the pH. So for that purpose, we are adding lime to increase the pH. So you need to find out all the cases in which you need to find out all the species, and we can find out the pH before and after lime addition. Everything is written over here. We have ammonium carbonate, we have ammonium chloride. You need to find out the pH. You can use Visual Mintech for that. I hope those who uh, those who are connected with this course, they might have downloaded this software and now they have hands-on experience in using the software. I will not show the software utility because while showing it in this Google Meet, it was misbehaving. So rather, I have kept screenshot for that. After solving maybe set of 8 questions, we'll learn about solubility equilibria in detail. Okay. We'll see the solution. So pH is 8.11 and 10.92. We have seen that sodium bicarbonate was 10 raised to power minus 2.5 molar. Ammonium chloride is this much. Calcium hydroxide we have added, we need to convert them into molar, so that the similar values we can feed in our Visual Mintech. So what is total sodium? Total sodium will come from where? This is the only source of sodium. Okay, there is no other source of sodium. So total sodium is fine. Total ammonia, from where the ammonia will be coming? This is the only source. So that is also checked. From where we'll get the total carbonate? Total carbonate, we have the only source. That is sodium NaHCO3. For total chloride, what will be the source? We have only ammonium chloride. It will dissociate and it will give us one set of 1 molar of ammonium, whatever is there, 10 raised to power minus 3 molar of ammonium chloride. From where we are getting total hydrogen? Hydrogen, there is no other source except for NaHCO3 in this example, because there is no calcium carbonate precipitation. Okay, so this is the only source from where we are getting total hydrogen. Just putting all those values and just putting entering solve, and we'll get the answer as pH 8.1. So this is before. Just putting everything in molar concentration. Simply, we do not have to solve anything, just putting all the values and we will get the values. So if you are using Visual Mintech with me, please have a look if you are getting the same solution. Okay, moving forward, what is happening after lime addition? We are giving out some calcium. So calcium hydroxide. So calcium hydroxide is CaOH2. So 2 times of hydroxide we will get. Okay. So OH is 2 times of hydroxide. So simple. What was total pH? H plus total was, initially we learned that H plus minus OH. This is what we learned initially. So we just got that, and we will put this value also in case of H plus. Then we can directly get the pH as 10.92. We can also solve this question using the simple method that we were using earlier. Based on W formation, we need to identify components, species, then component balance equation, mass balance equation, all those things we can also find out using this. But this visual Mintech is simple. It is a simple method that can help us to solve all kinds of problems. Okay, I hope you got this answer. So answer is 8.11 and 10.92 before and after lime addition. Coming to next question, this is also a real life question. We get all kinds of problem. A raindrop formed in a cloud passes over a smoke stack and absorbs 10 raised to power minus 5 molar H2SO4. That is how we get acid rain, right? The droplet next passes over a cattle feedlot and comes in equilibrium with ammonia gas. The urine, all those things will release ammonia gas into the atmosphere, right? So from there, this this raindrop has collected ammonia gas. The partial pressure is given. So it is in equilibrium with the atmospheric CO2. The pH and total dissolved N in the solution is. We need to find the pH and total dissolved N. This question can also be solved by simple method, by the direct method of using all those W things, and also the visual Mintech. So for this also we'll be using visual Mintech. This is based on Henry's law. In visual Mintech, whenever a gas is considered, we put it in form of partial pressure rather than molarity and all. We'll see the solution. Total hydrogen, it is coming from H2SO4. That is why we are multiplying it by 2. 2 into 10 raised to power minus 5. And total sulfate from H2SO4, we are getting 1 into 10 raised to power minus 5. Then we need to specify gas. As I told you, for the gases and all, we need to consider it in the form of partial pressure. Specify gas CO2, click on add button. Okay. This option we need to keep. So atmospheric CO2 pressure is considered as 0.0038 atmosphere. We know that atmosphere is made of 21% oxygen, 78% nitrogen, 3 to 4% of carbon dioxide. So like that. So we are considering it as 0.0038 ATM. We will simply click on add. Then we need to choose ammonia because it told that it is already in equilibrium with carbon dioxide. Now, after being in equilibrium with carbon dioxide, it went to the cattle field where it has taken up ammonia. So now we're talking about ammonia gas with the partial pressure. We will choose ammonia gas. Log K, all these values will come. All we need to put is the partial pressure in atmosphere in ATM. So then we need to click on Visual Mintech, run Visual Mintech, and we will get the pH values directly. These kinds of questions are there in assignment. It will be better if you can download the software and solve, so that it will be easier for you to solve the assignment question. I think this question was in last to last year's assignment, 2 years back. The same question was taken from there. Then we need to click on equilibrated mass distribution diagram. So this will give a mass distribution diagram and will get all the values. So this, how this diagram is coming, the one we were solving earlier, right? Equilibrium distribution diagram. We were making a box, then H plus, OH minus, all those things. So this distribution is coming from there, that we were doing manually. Now we can use Visual Mintech to solve the problem. Okay, so total dissolved N we can get from there. Okay, so this is very simple. So here, because there are multiple components like H2SO4, we have ammonia also, and we have CO2 also. And this was log C, and this was pH, right? Now what we need to do is, so earlier when there was just one compound, we were giving one CT value, something like this. CT value we were giving, right? So that was one CT value. Now do we have three compounds? So we have to give three different CT values wherever it is falling, CT1, CT2, CT3, whatever. And then, do you remember we were doing this initial position, then +1, -1 level? So using that equation, we can simply solve this kind of problem. Like we were retracing with the sparkling color last week. So we can simply retrace and solve this kind of problem. So that was based on diagram method. This is based on Visual Mintech, and for these kinds of questions, there is no direct method. You cannot just use any formula and solve this. That is not at all possible. People have developed formula, but that is really big with 10 raised to power 5 with degree 5 degrees. So it is not easy to solve them. And that too simultaneous equation, sometimes 4 equations simultaneously. Coming to next question. Two water at 25 degrees are in equilibrium with air, one at pH 9.5 and one at pH 6.5. When it is in equilibrium with air with different pH, means the carbonic acid system is different. The composition of carbonic acid, the species, different species of carbonic acid is different in different water. These waters are mixed in proportion of 1:5. Assuming that carbonate species dominate the acid-base behavior of the system and no gas transfer occurs, means it is closed system. When there is no gas transfer between atmosphere and the water sample, it is closed system. The alkalinity and the pH of the system we need to find out. Okay. Try to solve this question. This can also be solved by using the Tableau, and you can use Visual Mintech. Use either of the solution and you can solve this. We'll see. So alkalinity will come out as 5 into 10 raised to power minus 3 and pH is 9.56. So this is what we are getting from Visual Mintech after keeping all the values. Okay. So like here in this position, we were keeping all the values, right? Here like this. So we can put all the values and this is the thing that we are going to get. We will take in terms of concentration, and this software will give more exact value in terms of activity, but we do not need to bother about that. We are mostly doing it in terms of concentration because we are considering the water or the solution, and these, for simplicity, we are considering it as ideal solution. So it is not non-ideal, so it is ideal solution. So that's why we will be taking care of concentration rather than activity. We'll give all the values. We got total hydrogen, total carbonate, and alkalinity. Okay, so this is when the pH is 9.5. After that, the other pH, then we will mix the values, and simple by the dilution ratio, we can get the overall alkalinity. So we will get, after mixing, we will get overall alkalinity, overall H plus, and we can get pH also, overall pH and overall alkalinity. For the pH 6.5, these are the concentration. And we got all the total hydrogen, total carbonate, and total alkalinity value. The software will give everything. We just have to put this right concentration of all the components. For that, we need to prepare the W, but we do not need to solve the mass balance and other simultaneous equation. Since there are 1, 2, 3, 4, 5, 6, 6 values, so we need to solve 6 simultaneous equations. So we do not need to do that when there is software. There is a mixing ratio of 1:5, and now very simple, like if we consider alkalinity as A1 for the first pH, alkalinity as 2 for the second pH, and so simple, we need to multiply, like if we are solving alkalinity, so this is just dilution problem. Alkalinity first multiplied by, we have seen this ratio, right? Mixing ratio 1:5. So alkalinity first multiplied by 1, alkalinity second multiplied by the dilution ratio, and just dividing by the total mixing ratio, total of mixing ratio, and we will get alkalinity, we will get hydrogen, and we will get carbonate. Simple, we will feed all these values. Okay, step is written. Input the above calculated total hydrogen and total carbonate value in Visual Mintek. So it is not in equilibrium with the atmosphere. Okay, initially it was in equilibrium. Then we will keep the values in Visual Mintek of total hydrogen and total carbonate. After clicking run Visual Mintek, all these values will change automatically, and we will get the result. This question is also from 2023's assignment. Coming to question 4, it is saying in the question number 3, if the system is earlier here, it was not in equilibrium with the atmosphere. Now, if we are allowing it to be in equilibrium with the atmosphere, what will happen? There will be CO2 transfer from the water phase to the air, or vice versa. There will be CO2 transfer. Then, what is the pH of the mixture? first two steps will be same. There will be change in the third step where we have to just tick one value that there will be CO2 transfer. One tick will change the solution. Okay, so we'll see the solution. Yes, you want to say something? Okay, we'll see the solution. We have total H of 3.516 and total carbonate of this. So this we got from the previous question. Since now we are allowing it to equilibrate with the atmosphere, we will specify CO2 also with the atmospheric pressure or the default atmospheric pressure of 0.00038. You can put any other atmospheric pressure if you are in some other area. We can put atmospheric pressure like that, and just we will run visual Mintek and we will get the values when it is in equilibrium with the atmosphere.
Excuse me.
Yes.
So you are using software for the finding solution is Visual Mintech.
Yeah, visual Mintek. Sir
But
has taught this software only.
okay. So will you try to do directly?
These questions, yes, we can do directly. We can do directly, but it will take a lot of time. Like as I told you, there will be five, six equations to solve simultaneously. And in
Hmm.
the first few lectures, two, three lectures, sir has taught direct method only. So now we are
Hmm.
using shifting to software.
But SAR also using V Mintech only.
Yes, that is what I'm saying. In the
See,
first three
Manaki.
lectures, yes,
Ah, okay. Tell me.
yeah, I'm saying in the first three, four lectures, direct method was used,
Hmm.
okay, with simpler components. So that has already been taught. So now we are
Hmm.
teaching software. These days in
Okay.
real life problem, we are using softwares.
Yes. But in examination view, so we can't use the software and all, na?
Yeah, we won't give. Their question will
But
be very direct question will be there in examination. It will not be like you need to solve all these things. So
mm,
this is a PG level course. So this is required. The software is required to be taught to the students.
but see this question number three, if the system is allowed to equilibrate, this is very simple question.
Yeah,
You can do directly. It won't take much time.
yeah, yes, you are right. You are very right. This is very simple question. It won't take time, but the
Mm.
direct method has been taught in first three lectures. Now we are teaching software. We need to teach everything, whatever we have to the students, right? We are not here just for solving the examination. We are here to teach, to give
Okay.
ideas
But
to the
whatever,
student.
yes, I agree with you. But whatever you are teaching, na, that we can't.
Okay. So yeah, where were we? Yeah. So since now the system is in equilibrium with the atmosphere, we can give partial pressure of CO2 as well, which is 0.00038. It is by default, it is like this, but you can change it. So after putting all these values, we will simply get the result. You can use software for these kinds of this kind of problem. Instead of going through a long procedure of solving the problems, we can get simply by this software. Coming to next question. In the question number 4, after the equilibrium has been reached with the atmosphere, 1 millimolar H2SO4 is added to the solution to decrease the pH. Now system we are considering it as closed, means once it has reached equilibrium, we are closing the system. Okay, for example, we are taking beaker. Now we have closed it. There is no atmospheric transfer. Now what will be the final pH? So you have all those older values. Now you have to give the value of H2SO4 to decrease the pH. We need to find out the final pH. So after running Visual Mintek, we will get simple the pH after just putting this H2SO4 value. We will get the pH. Okay. Now H2SO4 is H2SO4 was 1 millimolar. So this is from what we get the older one from question number 4. Okay, the pH was 8.88. We have to just press this reset button. Then H2SO4 we will add 1 millimolar to bring down the pH. So total H is 4.7 and the 2 which is coming from H2SO4. Everything is in millimolar. Please be mindful of the units. Total carbonate is 4.89 from here from the older problem, and total sulfate 1 millimolar because we are adding. So this will give out 1 sulfate and 2 H plus molecule. And since the system is closed, we do not need to specify any gas. Now we will simply run Visual Mintek and we'll get the final pH values. And we can see when we solve, we can do 1 or 2 iterations. Here it has done 37 iteration to converge to a particular value, because these are set of how many equations? 1, 2, 3, 4, 5, 6, 7. 7 equations are there, and most of them can be 1 degree or 2 degrees or 3 degrees equation. So that was very hectic for us to solve. So that's why we are relying on software, and it has gone to 37 iteration within seconds. And if we are going to do this manually, it will take us years. And we will get the correct pH up to 3 decimal place. Coming to next question. Our solution is at pH 8.35 and it has reached equilibrium with the atmosphere. Now this is open system. Now place this solution in a closed system. Then the concentration of H2SO4 that must be added to lower the pH to 6. Now what is happening? We have a solution which is at pH 8.35. First, it is equilibrative with the atmosphere, means CO2 is coming. So there will be some change in pH, right? After that, so this was first system. Now it has came in contact with the atmosphere. Now we are closing it. Now there is no contact with the atmosphere and the pH is further brought down by using H2SO4. So we need to solve this question step by step. First, we know the pH. Second, atmospheric thing. We will get some values. After that, we just have to use H2SO4 and close the partial pressure of carbon dioxide. And we'll get the values. Okay, so this is the solution. First, we need to fix the pH at 8.5. Okay, all the steps are written very clearly. So first step one is that we need to fix the pH, because for the first system we knew the pH. After that, when since it is open to atmosphere, there it will be in equilibrium with CO2 with the multiple of 1, and the what was partial pressure, it was 0.0038 or 0.004. Okay, we need to run visual Mintech, and then we can print the result to Excel, and we can get total carbonate and total hydroxide. Okay, when we if we can put this result in Excel, and if we draw the graph, we will get some values like this. Okay, species with pH. So I hope you have seen this system for phosphate. For different pH, phosphate will have different species in the form of phosphate or HPO4 or H2PO4, like that, like carbonate system. We had phosphoric acid system also. So it gives different species at different pH. So from these values, we can get similar kind of diagram for any compound. It is easier to remember for one or two compounds, but there are many n number of compounds, and the mixture of compounds, we can get this kind of diagram for them. Now we need to reset visual Mintech, and since we have found the hydrogen and carbonate concentration, we will keep that. Now here, since we are going in opposite direction, we need to go to multi-sweep or titration menu, and we need to choose titration with the titrant with defined composition. So I hope you remember I was showing you this kind of diagram. Okay, so we need to add 1 molar H2SO4 for reducing the buffering capacity of water. Okay, so here it was fast, reduction in pH was fast. Then pH will be this side, and this is concentration. Then there was some buffering, then it was fast again, then it was some buffering. So this problem is similar to titration mixing problem. Okay, from the titration manager. So when we are solving it manually, we can give one or two steps, but here we can give multiple steps. Volume of titrant is 5, and volume of solution to be titrated is 50,000. For example, if we have a burette, we are putting some titrant. Okay, and we have a conical flask which is called titration flask. When we titrate it, what happens? How much solution do we take? 100 ml, 50 ml, 200 ml, like that, right? Let's say 100 ml. This burette is mostly 50 ml. So when we add the solution drop wise, so there is change in the volume. 100 ml will become, there will be change in volume. So this also changes the pH of the solution and the characterization of this solution that we do not consider normally. This, if we read the standard method, the latest edition is 23rd edition, given by EPA, Environmental Protection Agency, EPA. So if we will read that method, that is saying that we have to do all types of correction for changing the volume of the titrant because of what we are adding. Okay, but in this software, so there will be change, like if 2 ml is coming, there will be change of 102, like that, right? So In Visual Mintech, there is one option. We can choose the volume of solution to be titrated as much as possible. Like here they have chosen 50,000 ml. So that in this case, what will happen? With the change in the volume of the burette, there is no change in the characterization of the solution that we have in our conical flask. So huge volume is required if we want to follow the method. Otherwise, there will be n number of correction that we have to apply. We will never get the correct acidity, alkalinity, or BOD or COD, whatever you want. We will not get correct value because of the volume correction. So, but in Visual Mintech, we have a provision to take the volume of titration as 50,000 and volume of titrant as much less as possible. So here they are taking 5. We have the concentration of titrant and we can solve this and we can simply get all the answers. So H2SO4 is the H2SO4 needs to be added is approx this much, 4.55 and 10 raised to power minus 4 molar. So we can solve this problem in lab while taking a burette and all. We will not get any exact answer. At max we can go maybe 4 into 10 raised to power minus 5. That is also fine, but we will never get to that exact pH. And for some questions, for some kind of precipitation, we require to go to that exact pH. Otherwise, we will not get the desired result. And that is not possible in labs. What 4.5? We may get 3.5 also, because we have done this kind of experiment in our lab, and while doing the analysis in lab with smaller titrant volume of 100 ml or 200 ml, we were getting values upon 3.5. Okay, never 4.55, so it is way less. And see here how many number of steps they have done and how many we do, mostly 2 or 3. There is second method also. Similarly, based on Visual Mintech, we need to fix the pH, then specify gas as a multiple of 1, run Visual Mintech. So this is similar. Print the result to Excel and find total carbonate and hydrogen concentration. We got carbonate. Then we need to reset Visual Mintech and put total hydrogen and carbonate concentration. Now we need to fix the pH to 6. Run Visual Mintech again. Now we are fixing the pH. Earlier we were not fixing it. We were directly doing trial and error and getting to the pH. Now we have fixed the pH and we get equilibrium mass distribution. Equilibrium mass distribution is what I told you in the last class. So we will get the answer. Coming to second last question. Consider a solution having pH 8 and alkalinity 50 mg per liter as CaCO3. This solution is placed in a container having partial pressure of CO2. So it is open to atmosphere, okay. Then the pH of the solution of the container. This is very simple question. We have pH 8, we have alkalinity, partial pressure of gas is there. Now what will be the new pH of the solution? So alkalinity is providing the buffering capacity. So there will be some resistance in the change of pH. So what will be the new pH? Try to find out the solution of this one. We need to fix the pH to 8 and specify the alkalinity. Simple, run Visual Mintech and calculate these values. We need to follow a simple step. I have solved all these things in Visual Mintech and kept the screenshot for you to follow. So when you will solve this in Visual Mintet, you can check with the screenshots if the values are coming correct. I'll share this PPT with you so that when you do, you can check it by yourself. I have kept screenshots of all the figures. See, all the screenshots are there for every screen that we get, and I have marked also where you need to put the values so that you don't have to find anything in this Visual Mintet. Coming to last question. In question number 7, after the equilibrium, the solution with CO2 present in the container has been reached. So, if you are expecting questions examination, this kind of question may come. Okay, simple question. So, there will be two pH given of the atmosphere and the solution, and they will ask very simple question like a container is there and a solution is there. Something is there with some partial pressure, 1 atm, let's see. So, and here we have something of 10 millimolar of maybe H2CO3. So gas will be coming in or it will be coming out. This kind of question may be asked in examination, very simple. So no exchange is happening. So such kind of question. You can say if the thing is oversaturated or undersaturated or what. When we will learn solubility equilibria, we will see more such questions. So simple. The initial pH is 8 and the final is 4.8. Okay, it means pH has decreased. So CO2 is coming into the solution. How pH has decreased means acidity has increased. So this CO2 has been converted to carbonic acid, which is increasing the pH. When CO2 mixes with the solution, it converts to carbonic acid, which reduces the pH of the solution. You can expect this kind of questions examination. Simple, direct, no use of any software or anything. Okay, rest of the things, it can be contacted. So that is all from the presentation from the week 7. So I was planning to start solubility equilibria also, but it seems I'll stop here now. So I'll see you all in the next session. Thank you, everyone.